Hey there, I'm back. I didn't mean to pause the last video, but it's also a new day. Yesterday was Wednesday and today is Thursday, and I just got interrupted while I was doing the last video. But yeah, so anyways, if you remember where we were last time, I was confused about why an ion was not charged when I drew the Lewis structure. That's because I'm pretty sure it's not classified as an ion. Maybe, maybe not. I think it has the aqueous. Anyways, I chose the one that doesn't work for my example, but for the rest of them it does work. So I've chosen four ions right here to demonstrate for you how you can use Lewis structures to determine how many or what the ionic charge of an ion will be. Remember, a compound that has an ionic charge is a compound that is covalent, and it in and of itself has it. And the ionic charge depends on how many electrons in surplus or the opposite of surplus it has. I don't know what the opposite of surplus is. Like doesn't have enough. So when a compound doesn't have enough electrons, it's gonna have a negative charge because to complete all its like octets and whatnot, it's gonna have to bring in another electron, which is gonna give it a plus or a -1 charge. And the opposite for positively charged ions, I'm just gonna put another one on here. We can replace SO4 with NH4. When it has an extra electron, it's gonna want to donate it. So, sorry, it's gonna give it a positive charge. So let's draw a few of these just so you can get the gist of it. So right here, I've already counted out the valence electrons for each element, or each compound. Valence electrons. Bromic, I don't know, bromine oxide, I don't know. And then chlorate, oh, it's bromate. No, it's not bromate. I don't even know what that is. Boroxide. Chlorate, phosphate, and then ammonium are the elements we're going to use. Didn't count NH4, but let's just go. So bromine is going to be connected to an oxygen, and that subtracts 2. So we have 11 valence electrons to use. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, I hope you see what's wrong with this picture. Remember that the octet rule has to be completed when you have a compound. Problem is, we don't have enough electrons for, this. We don't have enough electrons for bromine to complete its octet, which means it's going to have a hole. This hole is going to be what makes it ionic, what gives it its charge, because it doesn't have enough electrons. So what it's going to do is it's going to try and grab an electron from a cation. This is an anion, because cations are positively charged, meaning they donate atoms. They lose, they lose electrons. They donate electrons, and this is where it gets donated to. It's because the negative ion doesn't have enough electrons, so it's going to try and draw one in. And yeah, and that's essentially what it is. We're missing an electron, so it's going to be minus. And when you have others that are like -2, that's because they need even more electrons to fill up. So let's go to chlorate, Cl. O, 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 O. Okay, so we've already subtracted 8, so 31 minus 8 is going to be 23. And all I have to do is fill in the electrons. We have 27 electrons in reserve, and we're going to see what happens. So, we'll count in Spanish. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Espere. 23. 31 minus 8 is 23. I don't know why I wrote 27 there when I said the other number. But anyways, as you can see, we went and we filled it all up, and then we got to 23, and what the heck? We're still missing an electron. We need an electron to fill this empty space, which means that ClO4 is going to have a charge, or its ionic charge is going to be -1. Now I'm going to double check that, just in case I was wrong, because if I'm wrong, it's going to be a problem. Boom, boom, boom. Boom. Ions to know and friends. Chlorate, chlorate, chlorate. Yeah, oh, it's perchlorate. Okay. Well, yeah, it has a -1 charge. Same as all the other chlorates, chlorites, and whatnot. Yeah, so that's how you know. We can skip PO4. Uh, Actually, PO4 has 3, if I'm not wrong. So let's do that one so we can kind of just get an example of ones that have extras. P, 1, 2, 3, 4. 2, 3, 4. So that's -8. 29 minus 8 is going to be 21. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. No, 13, 14, 15, 16, 17, 18, 19, 20, 21. Uh-oh, looks like we have a problem. We have spaces for 3 electrons. This electron needs to go here, an electron here, an electron here. Yep, so that's a problem. So we know that PO4 is going to be like this, PO4, 3 minus. And it's going to have to bond with enough cations to fill in those spaces. So NH4, as we know, actually let's just try. NH4 has its own charge. So let's see how many NH4s, ammoniums, we're going to have to bond with phosphate for us to get what we need. I just got a message. Oh, finals. Awards. The heck? See, bonus point. I don't even know how you get an award for excellence. Like, you're just a student, man. Anyways, NH4. H. One, two, three, four. Ammonium has, so nitrogen has 5 valence electrons. Sorry, 5 valence electrons, and then we get +4 from the ammonium. I mean from hydrogen, so that's going to mean it has 9 valence electrons. And we've already used 4 right here, and hydrogen can only hold 2, which means we have an extra electron just floating around, and he's just hanging out, which gives NH4 the charge of +3 or +1 as +1. So looking at this, if ammonium has 1 electron to give, and PO4 needs 3 electrons, how many ammoniums is phosphate going to need? It's going to need 3 of them. So the compound will look like this. PO4, and then parentheses, NH4, 3. That would be ammonium phosphate. So I think the ammonium goes first, but that's okay. And yeah, and that balances out with the amount of electrons, because phosphate needs 3 and ammonium is going to give 3. So another note, we learned that there are exceptions to Lewis structures, that some structures will not have enough valence electrons for their center, and others will have too many valence electrons. So the ones that have, or won't have too many, those have too many connections around them, uh, are actually different from this. So this is when elements are electron deficient, but have enough electrons to satisfy all of the outers. So valence electrons come from the outer electrons that the elements are willing to share. However, when the center atom has problems, like when it doesn't have enough or when it has too many, that's when it's an exception to the Lewis structure, not anything else. So, for example, I think boric trioxide, BO3, is an example of this. So, oxygen is 6, boron is going to be 4. Yeah, 3. So, that's going to be 21. So, check this out. Boron, I really hope I got the element right. BO3, 21, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That's 600 is 18, plus 1, 2, 3, 4, 5, 6. Wait a minute, something's wrong. I think this is an ion. Okay, that example didn't work, but let's just leave it said that boron is one of the elements that can experience a lack of 8 valence electrons, or 8 electrons in its octet. You see how it only has 6 right here? Um, and it's fine with that, assuming this was an element that actually worked. The reason for this being that boron is so small and high on the periodic table that it actually doesn't really care. In the same way that fluorine will, if it's on the outside, will not die valence electrons to the middle sometimes. But I can't remember any examples of that. Anyways, that is ions and Lewis structures. I hope that was informative, because it certainly helped me. Anyways, stay frosty.